Hello everyone, welcome back to the part 2 of the Numpy recitation. Let us look at how to access and play around with Numpy arrays. So let us consider a three-dimensional array of shape 4, 5, 6. We interpret this to be as 4 batches, each containing 30 elements spread across 5 rows and 6 columns. Now, if you're looking to locate an element in the first batch, position in the fourth column of the third row, you can simply reference it as n of 0, 2, 3. Keep in mind the zero-based indexing. Thus, for the first batch, you start with 0. Similarly, when targeting the third row, indicating it as 2 and so forth. If you're not looking for just a single number, but rather want to extract specific portions of the array, then the approach is slightly different. For instance, if your goal is to retrieve all the elements in the first batch, you would use the notation n of 0 or n of 0, followed by two colons. This signifies accessing all the rows and the columns of the specified batch. Likewise, for slicing across multiple batches, you employ the notation n with colon 3, 4. The operation will fetch all elements located in the fourth row and fifth column across the batches. Now let us consider a scenario where you're not interested in obtaining all of the rows and columns sequentially, but rather specific columns at certain intervals. In such cases, Python allows you to slice arrays using the formula involving start, stop, and step size. In the given example, you're working with a three-dimensional array, and the slicing operation involves selecting elements from index 0 to the end at a step size of 2 in the first dimension. This slicing mechanism takes care of the interval specified in the syntax. If you need to perform similar operations across different dimensions such as batches, rows, and columns, you can easily adapt the syntax. In this case, it will take rows 2 to 5 and columns at an interval of 2 starting from 1. Let's look at the process of modifying the data. If you intend to make changes to the data in place, it is definitely possible, but it is also advisable to create copies to safeguard the original data. To achieve this, you can utilize the np.copy function to generate a copy of the array. Suppose you wish to alter the specific values to 2, 4, 1. In that case, you can easily accomplish this by assigning the new value to the respective location. So in our case, we have assigned a value of 0.005 to the desired location. It's worth noting that you can verify whether the values in the two arrays remain consistent both before and after copying. So prior to copying, we see that the values are same, while after copying, these values aren't the same. But what if you want to modify multiple values? So if you want to modify an entire row or an entire column, then you can simply do n copy of 2, 3 is equal to whatever value you want to give. In our case, we have chosen the value of 0.5. Or you can also give a new array of the same shape that has to go into that particular location. So in this case, you can see that before modifying the values, you have a different array. And after modifying, all those numbers are essentially changed to 0.5, and they are not the same as the initial array. Now, let us look at pivoting data. So, pivoting data involves reshaping arrays into different dimensions. The key thing to understand is that the total number of elements must remain the same when reshaping. For example, take a 3D array with a shape of 3, 4, 5. So this array contains 3 into 4 into 5, which is 60 elements in total. We can reshape the array into any new shape we want as long as the new shape also contains 60 elements. So we could reshape the array into 2, 6, 5, as this keeps the total elements as 2 into 6 into 5, which is 60. But we could not reshape the original array into 2, 7, 8, because 2 into 7 into 8 is 112. This exceeds the original 60 elements, so NumPy would throw an error. So the main rule is that reshaping is possible as long as the product of dimensions matches before and after. and this ensures the total number remains identical. Now let us look at reshaping to a different number of dimensions. So reshaping a 1D array into higher dimensions is possible by specifying the new shape as long as the total number of elements remain the same. For example, if we have a 1D array which is generated or created using np.arrange, and we see that this array consists of 120 elements, we can reshape it into 3D array with a shape of 3, 4, 10. This is because 3 into 4 into 10 equals 120 elements. So NumPy will reshape the original 1D array of 120 elements into a 3D array that consists of 3 batches, 4 rows per batch, and 10 columns per batch. The underlying data remains the same, only the interpretation of the dimensions changes. The key thing is that when specifying the new shape for the reshaped array, the product of all the dimensions must match the number of elements in the original 1D array. And you don't have to stick to three-dimensional arrays. You can also reshape it to a two-dimensional array as seen, or pretty much any n-dimensional array as long as you keep in mind the rule that you have to follow. Now let us look at how to transpose the arrays. Transpose essentially swaps the rows with columns and vice versa, but this applies specifically to 2D arrays. So in the original array, we see that it consists of 5 rows and 10 columns. So calling np.transpose or x.T transforms the first column of the original array, which is 0, 10, 20, 30, and 40, and makes it into the first row of the transformed array. Likewise, the second columns becomes the second row and so forth. Now, let us look at what happens with three-dimensional or multi-dimensional. Let us look at what happens with three-dimensional or multi-dimensional arrays. So consider that we have a new array W which has 3 batches, each containing 20 elements. If we use np.transpose without specifying the axis, it is automatically going to swap the number of batches and the column index. In simple terms, if the original shape was 3, 4, 5, the transposed array will switch 5 and 3 while keeping the number of rows the same. So we see the shape of the transposed array and it is 5, 4, 3. So let us now specify certain axes and see what happens. So if you give axis as 0, 2, 1, it means that you are keeping the 0th axis as the same and you are swapping the first and the second dimension. And also the original shape was 3, 4, 5, and this becomes 3, 5, 4. So I'm going to leave it as an exercise for you guys to figure out how exactly the elements are changing. But as long as you understand how to specify the axis parameter and how the original shape and the new shape look like, you should be good. Now let us talk about flattening of arrays. This is an important concept as you would often do it at the final layer of your neural network. You will use this in P1 and also in P2. Flattening means turning an array with multiple dimensions into a single dimension. For example, you have a 5, 6 array and you use flatten operation on that, it will basically ensure that all the rows are stacked on each other and converted into a 1D array. The order of the elements in the new 1D array is the same as that of the original 2D array. So if you intend to flatten along the columns, you essentially give capital F as the parameter and you will see that it now forms a 1D array where the elements will be same as moving from one column to another. So you guys can test it out by comparing what the original array looks like and how the new array that's flattened along the column looks like. You can also flatten arrays row-wise by calling dot reshape and giving -1 as the parameter. Now let's look into the concept of squeezing and expanding arrays, which are particularly crucial in the concept of your P2s, especially when dealing with reshaping and ensuring compatibility of shapes during matrix multiplication. Squeezing as a fundamental operation facilitates the reduction of dimension by eliminating a specified axis, provided that the axis has unit length. The pivotal condition for successful squeezing is that the product of the shape before and after must remain constant, thereby preserving the overall number of elements within the array. So consider the original array which has a shape of 4, 1, 5. By employing np dot squeeze function, we can effectively drop the axis of unit length, resulting in a new array that consists of a shape 4, 5. The operation is permissible because the condition of unit length is satisfied. However, let's contrast this with a scenario where suppose the original array had a shape of 4, 2, 5. Attempting to squeeze this array would be futile as it fails to meet the required condition of having an axis with unit length. So you can also give a specific axis along which it has to be squeezed. Again, as long as it satisfies that one dimension is of unit length, you can provide that dimension and have the axis array squeezed or reduced in dimension by removing that unit length axis. You can also unsqueeze or expand NumPy arrays, which basically adds another axis in specified position. So again, the axis that is added is a unit axis. So let's say you have an array of shape 4, 5, and if you do np dot expand dimensions along axis 1, so this is the 0th axis, the new first axis is going to be 1. You can also add it in multiple places. If you add an axis 0, 2, the 0th axis becomes 1 and the second axis becomes 1. Remember that all of these are zero indexed. So this brings us to the end of the second part. In the next part, we'll talk about how do you combine data and some common math operations.